Hello to Computational Chemistry. It's Ismail Bedran again from An-Najah National University, and today we're going to talk about a tutorial using ORCA. So again, it's Ismail Bedran, and for me I have almost 10 years of academic experience. I am associate professor of physical chemistry, right now working at An-Najah National University in Palestine, in Nablus, Palestine. I have almost around 30 peer-reviewed papers with an H index of 12. I have graduated few students, participated in several international conferences. I have more than 16 years of teaching experience, and have also some professional academic diplomas. So for today, we're going to give you a tutorial on using ORCA as a computational chemistry software. As I said, ORCA is an open source computational chemistry software, so it's different than Gaussian for say, because Gaussian is paid, but ORCA is open source. You can download it from the website and install it to your computer and use it for free. Right now we are with ORCA 5. I think that the version is 5.04. So the software is quickly developed, and now it's well established. Before you jump into these type of tutorials, I warn you, and I need you to have the following. So first of all, you need to have solid foundations in organic chemistry. So basic organic chemistry courses like 1 and 2, that's going to be good for you to refresh your information in organic chemistry. Quantum chemistry is a must. You don't want to do computational chemistry without knowing the knowledge. So an introductory course in quantum chemistry, that would be good. And also a course or basic knowledge in computational chemistry, that would be also an asset. This is a heavy tutorial, and I advise you to probably watch or learn about basic computational jobs before you jump in. I have already a computational chemistry Gaussian optimization and frequency tutorial in YouTube. You can watch this one or similar ones before you jump into this one. Also, I'm expecting basic knowledge with using Windows, a little bit of Unix commands if you want to use Unix, and the program Avogadro. This is the program we need to draw the molecules and prepare our input jobs, as well as Excel. Microsoft Excel is really important here. The plan for today, we need to install the following programs into your computer. First, you need to have Avogadro or any program that you might use as a GUI, graphical user interface. You need ORCA 5 installed in your computer, or just in my case, I am having it on an HP servers, high performance computing server. Also, if you want to use the ORCA with the server, you need Bitvice or any SSH protocol program that connects you with the server. We might need the ChemCraft to visualize the frequencies, because right now Avogadro is not compatible with ORCA 5, even with the Avogadro that is designed to do that. I'm having still troubles doing this, so I'm viewing the frequencies using ChemCraft. There is an improved version of Notepad. I'm using Notepad++. That's a program, a very nice tool to deal with text files. And also, in this specific tutorial, I'm going to show you how to use and run jobs on the T3PS server at An-Najah National University, which is the university I'm working on right now. And of course, this server needs credentials, so you need a username and password to use the server. Otherwise, if you are not a member of a university or you don't have a server, you can actually install ORCA in your computer and use it, but it's going to be slow, of course. The reaction that we are dealing with is hydrogen elimination from monomethylsilane. I'm going to show you how to optimize the reactants products, and then we're going to run after the transition state. We will locate the transition state, and then I will show you some thermochemistry calculations. This is the reaction that we are dealing with. So we have monomethylsilane, a very basic classic reaction here. We're taking hydrogen out of the silicon side. So this is, of course, this can undergo several reactions. You can have one reaction from here, 1 H2 elimination from the carbon. You can have 1 2 elimination, so one hydrogen from here, one hydrogen from there, to form silane. But the one we are dealing with right now here is 1 1 elimination from silicon to form silane, or silane if you like to say it, plus hydrogen molecule. The good thing about this reaction is that everything here, including the transition state, proceeds at a singlet surface. So this is a singlet. Silane also, luckily enough, there are singlet in their ground state, and of course the transition state and the other products are singlet. So first of all, Avogadro, Avogadro free cross-platform molecular editor. You can just download it from the website, Avogadro website. There are two here. There's the 1.2 version. There's Avogadro 2.0, but it is not very functional right now. You can go with this one, 1.2. I think I have it here in my computer, up and running. So this is Avogadro program. So before you jump into this tutorial, if you have not used Avogadro before, I advise you to stop and learn Avogadro from YouTube or any other thing, because I'm not gonna show you how to use Avogadro at this point. So the other one is ORCA, and of course if you just Google the word ORCA, you will find these dolphins. And what we need is the ORCA computational software. So ORCA computation chemistry. ORCA right now has a forum. It's actually a very good forum with access to several questions and several things. This forum requires a username and password. So right now I'm logged in, and under downloads you have all the things that you need to install ORCA. So you have the last version of ORCA 5.04. You can install that to your computer, and also the manuals. And this is Avogadro also for ORCA. You can also download it from here. For this tutorial, I'm gonna use the ORCA on the server. If you want to use the ORCA on your computer, ORCA comes with a very good manual, and again it's version 5.04 here, and it teaches you. It's very actually organized and a nice manual. And here you have all the information. Okay, I think there is a section about calling the program, and then you call the program, and by saying ORCA, then the input file, and assigning the output file, and that should work nicely in your computer. So you can give it a shot if you like, if you don't have a server. But for me, as I said, I'm gonna use the server. Bitvice also, you need that for the server. So if you Google Bitvice, a client, that's the one. You need to download this as well, okay, and install it in your computer, up and running. I have it here myself installed. So this is Bitvice. It looks like that. What else we need? So we need also Notepad++. So that's the program I told you about. It's a must actually for people who are working with programming or computation chemistry. So I have the program here also installed on my computer. It looks like that. It's better than the classic Notepad provided by Windows. And finally, for students or members of ANU, An-Najah University T3PS server, you need a credential to do that. So you can contact me and have a username and password, and we can arrange for to access the T3PS server. Once you have that, you go to Bitvice and you click here t3ps.najah.edu. That's the name of the server. You can put your username and password here and just click log in. That's the regular way to log in into any HPC high performance computing server. So now it's working. It opened me the SSH window. So that's now I am on the window. If you remember, in the old days we used to say CD, that's a change directory, and then you call the directory you name. You just need to have some basic knowledge of Unix commands. So I'm not now on my computer, I'm actually using the server, and ls means list files, so you can learn about that basic commands through the internet. And here are my directory. So this is the file, the jobs that I'm actually running right now. So this is my computer to this side, and this is the remote or the server itself. You can transfer files from here to there, back and forth through this file window. Back to our plan so we don't get messed. So again, before you start, make sure to have all of these installed: Avogadro, ORCA, Bitwise, Chemcraft. Oh, Chemcraft, I forgot to tell you about it. So again, also it's very nice program. Chemcraft, you can download it as well. It's also on my computer. Now let's jump and build ORCA files or input files for these guys. So I'm gonna start drawing the monomethylsilane, which is MMS. Before you start, you can click on this one, the optimization, and click start. That will help you doing the molecule. Going back again to the draw molecule, you have carbon, so click once, and now choose silicon. Silicon is not here, so you go others and click the silicon, which is right under carbon. And now I have silicon in my hand. You click here, you see here it's optimizing as you go, okay? But this optimization is done with molecular mechanics, which is a primary optimization. It's not an actual optimization. You have to do the actual optimization using the computational chemistry program. Sorry for that. So now I have what here? I have, and now we need to get these two out. So that's my first reactant. So I'm gonna go with extensions and then ORCA and generate ORCA input. For now, you can use this. I'm gonna this window here. So I'm gonna choose geometry optimization, and you can choose the for MMS it's a closed shell, charge 0, multiplicity 0, multiplicity or sorry 1, it's singlet. And you can use the basis set. I'm gonna use this one, def2 tzvp. That's a very good basis set. And you know what I'm gonna do here, I'm gonna just copy this and I'm gonna show you what I'm gonna so you know what I'm gonna do here is I'm gonna stop using this window. I'm just gonna take this input file, because what I need actually is only the coordinates. So I'm gonna take this file and put it in Notepad. So that's Notepad++, and I'm gonna save it here. Now before anything, we need to save this file. So file, save as. So as I said in my previous video, you need really to get organized here. So I'm gonna make a folder. We'll call it ORCA _ tutorial. You can call it whatever you like. And you don't use spaces, remember. If you have not seen my first video, you should stop and see it now, because there are so much tricks to that one. So ORCA tutorial, and for this for ORCA it's better actually to put everything in different folders. So I'm gonna make a folder for MMS, okay, and I'm gonna call this MMS _ opt fric, and I'm gonna give it a number 01. So just call it input, ENP. ENP, that means input. Okay, so that's saved. So now I'm gonna show you like an input file template that I use for my jobs. For this one, you give it a name. You can call it whatever you like. That's optional. Opt fric. This hash means it's a comment. So the existence or inexistence of this hash means nothing. Each input command starts with an exclamation mark like that. So now this tells you this actually tells the program to optimization to optimize the molecule, followed by frequency calculations. RKS means it's a closed shell. This is the functional that I'm using, M062X. So actually we have a recent paper discussing the best functions for computational chemistry. The paper is published on the International Journal of Quantum Chemistry with Wiley. This is the paper. You can download and read it from here. In this paper, we actually found that the functionals, the Minnesota functionals produced or developed by the Turler group in the United States are really well performing. These are the M062X, MN15L, and so on. so you can enjoy reading this paper from my work. So M062X, that's a very good functional, and this is the basis set. And according to ORCA, you can use the auto auxiliary basis set. So you can just copy this file. You can actually copy this line into here with my MMS file. Okay. ORCA can proceed with parallel or single processors. So since I'm working with a processor, I'm gonna use 24 nodes. That's 24 computers. So I'm gonna copy this file copy this line here as well, and end should end the first part of the file. We might not need this or that, so I'm gonna just call this opt-fric. So now my file is ready. This is the file for MMS. This is the file. This is the input file that I generated from Avogadro. I just replaced the few first lines with this. I'm gonna close this and save that. So now I have MMS opt-fric _01 input file, good to go with my ORCA. This is the first line. You can call this whatever you like. It's optional. Now I'm asking opt-fric with this functional, with this basis set, as simple as that. Okay, and I'm gonna use 24 processors. If you're doing this in your computer, you can do something else. XYZ, that's the coordinates for the molecule. 01, that's a 0 charge, and 1, because MMS has no charge. It's a neutral compound. It's a neutral molecule. 1 means singlet. So, and this is the coordinates for the molecule. Don't forget that this starts with a star, ends with a star. Let's repeat that again for H2 molecule. So what you can do, you can just click a new file in Avogadro, and then this is hydrogen. Although I clicked here, adjust hydrogen, I don't know why. So again, start optimization. This is a very good hydrogen molecule. You can again extension ORCA, generate input file. I need only the coordinates. Okay, only the coordinates. I'm gonna close that. Close everything here. Go back to my folder, to my original folder that I put the MMS here. I'm gonna actually copy this folder, so I'm gonna click Control, drag with the mouse. That will make him a copy. I'll call this H2. This is how to speed up and enjoy working with your files. So I'm gonna, instead of MMS, I'm gonna call this H2. Same thing, double click, just replace that. Click that, paste the H2. That's it. Voila, save, ready. See that? Fast. So I have now H2 with the same inputs. What else we need? We need a silane. So we can go back to MMS. I don't know if that will be read by this. Let's try. It's Avogadro cannot read input files. I don't know why. So I'm gonna do this again. It's okay. So start and then draw carbon. I'm sure that you can find a way to allow Avogadro to read input files or import the XYZ if you like coordinates. What I'm gonna do here, I'm just gonna take this hydrogen out. Okay, so click on this arrow. Okay, so this and this should go out. Now I have a silane. If you are not following, we can go back to this PowerPoint. So here is the silane. Okay, it's a methyl with a silicon and only one H on it. That's this. Okay, this is silane. I'm gonna you don't have to save that file as Avogadro. You can just generate. By the way, Avogadro generates files to bunch of computational chemistry programs, including Gaussian, QChem, and all the others. So generate data file. Again, coordinates. The charge is 0, singlet. That's not always the case. If you have a cation, anion, radical, it will be a different story. But for this, it's a singlet, luckily enough. So same procedure as before. I'm gonna copy this, call it silaline and change also the name silaline, sorry, and copying the coordinates here instead of those. So I have 3 files, one for MMS, one for the silaline, and one for the hydrogen. Good to go here. You can always double check your work. This is the hydrogen, this is MMS, and this is the silaline. Okay, it looks good. 4 H's, 1 silicon, 1 carbon. Now let us throw this to ORCA on the server before we move on to that transition state. For people who are working with the server, so for people who are going to work on the server, on the ANU server, we prepared 3 files to process the work. I am going to post those files on the website. So I'm gonna copy these files here. One is called a_parallel. These are just script jobs, okay, to tell the program to load the file and run it, okay. And for each folder you need to copy the files. You can actually put all the jobs in one folder, but that will be less organized and you will have troubles reading the files and so on. So for ORCA it's better to put each job in a folder. So now I have 3 folders with all of these files, okay. So the input file and submission files. So now you go back to the let's just get some windows closing here. And by the way, I'm using Camtasia Studio to record my lectures, if you are wondering which program I'm using to record my lectures. It's a very nice little piece of software. So now I am here on the server. I'm going to make a folder to run my jobs on it. Like this is a project, right? So for each project you need a folder. I'm gonna call this MMS2. I have already MMS1 from previous jobs, so I'm gonna call this MMS2. And for this, it's an empty space here. So what you go to your Windows Explorer, choose all of these three folders and drag them into this window. Okay, you can do this also from here. Now it's copying. I think it's finished. I have a good internet today, so now the files are ready. Okay, you need to copy this path, so Control-C here. You go to the shell and go CD this, CD, sorry. You go CD, that means change directory, and then right click. Right click, that will paste the path into here. Okay, and click enter. So now we are actually inside that folder. Well, actually we need to go inside each one. So H2, so again Control-C, CD this. Now I am inside the H2 folder. So if you go ls, list files, you see actually the files that are inside the folder. And simply what you do is you run this command, a.parallel.sh. That's the file, that's a script file that we prepared to tell the server to go and run this input file. If I click enter, something happened here is that says permission denied. Maybe some of you will find a solution for this problem, a permanent solution. But for now, what we need to do is we need to allow access to this file. So right click on it, permissions, and then you need to allow the execution of that file. So click all of these. Again, right click, properties, and you go to permissions and put a check mark on everything here. Going back to the server, on a Unix shell, if you click the upper arrow, the arrow to the top on the keyboard, that will just repeat the previous command, you see? So up and down, I'm gonna repeat the command, and voila, it's working. So it says one job submitted to the cluster. and it has a number actually 1803. I think I remember Condor Q, because this one is using Condor. Condor Q will list you the jobs that are running. Here my username is ibadran. It looks like I have a job running so far here. If you refresh here this window F5, you see something is happening here. So that means the job is running. While this is finished, I'm gonna go and do the same for the other folders. So CD, I'm gonna go into the MMS folder, Control C, change directory, right click. Now I am on the MMS folder. I have already the A parallel file here. So I'm gonna do the same thing. Up arrow, call the A parallel.sh, enter. Oh, permission denied. Oh, bad. Copy this, CD, right click. I am now in the silent folder, A parallel. I have done this before on this folder, and if you look here, after finishing the jobs, you will have, let's say for the H2 job, you'll have a lot of files, XYZ, out, whatever. What you need from here is only the log file. Okay, that's the output file. So I'm gonna copy these log files into my computer. The same way you copied before, you copy it now here. So H2, just click the files, control, or you can call it the locations, copy them back into your computer. So finished copying, because this belongs here, so I'm gonna put it here, and this one here looks here. So now the jobs are finished. You can actually open the log file on Avogadro just by clicking on it. That's the optimized molecule. You can right click and say edit with Notepad++. This is the output file. Looks nice. Actually, ORCA people did a really fantastic job formatting these output files. If you go all the way down, it tells you just like Gaussian, it tells you that it's finished. It gives you the time, location. ORCA terminated normally, happy life, no errors, so good. You have to do that with all the files and make sure that they are finished correctly. The next part is the thermochemistry, so we'll take a break and come back to watch the thermochemistry. Now, before we jump into the thermochemistry part, we need to understand that this reaction has reactants, products, but also it has a transition state. So, for this simple reaction, we're expecting that these two hydrogens are gonna come out in a conserved way. Of course, this reaction can proceed with a radical reaction. That means you rupture the first hydrogen first, then the second one, followed by a recombination in the gas phase. But let's assume that we have a concerted simultaneous concerted elimination of H2. That means these two hydrogens will just combine and fly as a hydrogen molecule. In this case, what I'm expecting, that shape of the transition state, something like that. So you bring this hand tool and you just bring these two hydrogens a little bit together. The distance between these two atoms right now, if you click the measure tool, it's about 2.4 angstrom. And a hydrogen molecule will have a distance of around half angstrom. So what I'm going to do, actually, I'm going to bring this hand tool, and I will just bring these two hydrogens close to each other's and far away from the silicon, hoping for this would be a good guess for a transition state. Okay, you can try. Finding transition states tricky business, so you can try this. I have made them a little bit away from the silicon, group them together, okay, and then I'm gonna save these coordinates again. ORCA, generate input file, bring the coordinates, and similar to what I did before, I have prepared another file with a different folder called TS OptimFric. I'm gonna paste the coordinates of the transition state, or the guess of the transition state, and save that file. But remember, we're not optimizing a molecule here, we're optimizing a transition state. And for that, what you need to do is actually, you need to use the command opts. Also, ORCA advises to use the tight SCF slow conversion file. So I'm gonna just copy this line and put it here. So this will be optfric ts. Gonna save the file. Now let's go over that. So it says tight SCF. That's a better way to a more accurate way for optimization. This might be optional, by the way. Slow conversion, I assume this will be also taking care of the steps for the conversion. You can try this actually without these two words, but here is the important thing: is TS. We're not optimizing a molecule. We're looking for a transition state with at least one, with one and single one imaginary frequency. If you don't know what I'm talking about, you need to go back and understand the conditions for a transition state, and from your course or from another video. RKS, this is also a closed shell because it's a silane, and you must actually use the same functional and the same basis set for everything. If you are not doing that, then in that case you're doing something wrong. So here the file is ready, okay, and I'm gonna save it, put it in the server, also run the job as I did before, and getting the output file. The next step of this tutorial is finding the energies. Okay, now from your chemistry course you understand that electronic state of a molecule, it has a vibrational levels. So that's why we need to calculate the vibrational frequencies of each molecule and each species in this project, which we did already. We asked for optimization and frequencies. The first vibrational level is called the 0 point energy. So of course that this is not to scale, but you have to know that this is the first level here is called ZPE, 0 point energy for the reactants. You have also ZPE for the transition state, and the same for the products. If you have more than one products, you have the same thing. I'm assuming this is an endothermic reaction because the products are higher than the reactants. So here this level represents what we call the H correction, or the enthalpy correction for the electronic energy. It is higher than the ZPE, and you might have other corrections at different temperatures. So this one would be the enthalpy correction at room temperature. Okay, so first of all, to deal with thermochemistry, what you can do is you can subtract the electronic energy, which is the red line, minus the electronic energy of the reactants, okay, and that will give you delta E at 0 Kelvin basically, which means nothing. Okay, it's a number that is far away from any experimental measurements or results. The better thing to do is to add the 0 point energy. 0 point energy, by the way, the electronic energies, the blue line and the red line, are always negative. Okay, the ZPE and the H correction, they're mostly positive. Okay, and so if you add the ZPE to the electronic energy of the reactants, and you do the same thing for the products, ZPE plus the SPE of that, and you subtract these two numbers, you will get something called delta E standard, and that means it's the energy difference with ZPE correction. It's a good number. Some people, they use it to compare with experiments, but remember that would be at 0 Kelvin. Now what you can do is you can add the H correction and the ZPE to the single point energy. So you add all of these together. Now we are here, okay, You do the same thing. So the difference between this level and this level now, if you can draw a line from here to there, that will be your delta H. Okay, delta H naught, which is the energy difference, or the energy difference with the enthalpy correction and the ZPE correction. You can actually do something better, which is you find something called the entropy correction, okay, or the Gibbs free Gibbs energy correction, which could be somewhere here. Okay, it's another correction. You can add it to the previous ones, and you can do the same thing here, and then you draw a line between this level here and that level here in terms of Gibbs free energy, and the difference would be delta G. So in general chemistry courses, they tell you about reaction energy, okay, or delta H simply, or they call it energy difference. But in computational chemistry, you have to be very specific about the meaning of that. When you say energy, reaction energy, what is it? Is it in terms of delta E, or delta H, or delta G? Is ZPE included or not included? You have to be very specific when you communicate with your readers or with your project leader about your results. You can do the same thing with the transition state. So that's the activation energy, and we denote with a double dagger here, or a star sometimes. So if you find the difference between this level and that level, which is the ZPE plus SPE here, ZPE SPE here, you find the difference, that will give you delta E activation. And if you do that with the enthalpy correction, it's going to be called delta H activation or delta G activation. In my first experience with computational chemistry, I was actually correlating delta H with experiment. But recently I found that it's better actually to speak in the language of delta G, because it includes the entropy correction. So you can go to my papers and see in which contents I was in this or that. So let's jump into the practical part of that. Okay. First, you need to fire your Microsoft Excel. Okay. And now you have here your MMS. You have your H2 reaction. You have you have your transition state. You have your silane molecule as a product, and you have also your H2 molecule. So this is your products, this is your reactant, this is your transition state. I'm gonna just click everything and do everything in is centered. Now what we have here, we have again, it's advisable that you attend a computational chemistry course to understand what I'm saying, but for people who know that, so we have the SP energy, the electronic energy for everything. We have the ZPE. Okay, I have also the H correction. I'm not gonna deal with G correction for now. The Gibbs. I'm gonna only deal with these three things, and of course each one is in HAR3s. Okay, or atomic units. So you must put the units here as well. So our Excel is ready. Now we need to go to the files. This is the MMS file here. I'm gonna open it with Notepad. The log file, of course, is big. So what we're looking at is this. In ORCA, the single point energy is called electronic energy. So if you copy this and go to your file and Control F or search for this word, you will have only you will find a lot of entries that says electronic energy, because they correspond to different optimization steps. But what you need to find is this one, is the electronic energy with the 3 dots. So actually if you click here, this is a very good practice, and search for it, that's only one number. You see I'm clicking enter here in the find window, and I have only single value. So I'm gonna copy, and EH means the HAR3s, the atomic units. So I'm gonna copy this number into my Excel for the MMS. So right here, I have to copy the whole number. Now for the next one, in Gaussian, sorry, in ORCA. So the next one in ORCA, it says 0 point energy. That's easy to find. So copy, and then look for the word 0 point energy. Here it is. Actually, it's under. Oh, it's right here. So you can copy this number into your Excel for the MMS. And for the H correction, that's actually the trouble, because there are so many things that say thermal. Is it this one? Total thermal correction, total correction. It's very misleading here. But I'm telling you that actually in ORCA, the correct one is called total thermal correction. So total thermal correction is the one you need. So going back, I'm gonna close this Avogadro. So going to the file and paste this. So this is the one. Total thermal correction is the number you need for this thermochemistry calculation. So I'm gonna copy this and paste it here. You have to open each file and do the same for TS, silane, and H2. Okay? And copy these numbers. For me, I have prepared an R. R is a statistical programming language to prepare a script that reads all of these numbers automatically. If you're using Python, you go ahead and build your own, and that will bring all the numbers ready to a CSV file and to Excel. I have arranged or brought all the numbers here into this file. So this is the file list. I have 4 files. It looks different here than the previous file. You can do them, of course, in the way you like. I have here the electronic energy, ZPE, the thermal correction. I have also the entropy correction, which actually I don't need right now, so I'm going to delete that. Actually, you know what? I'm going to keep it, and so to tell you how to do that and for the Gibbs free energy. Now, the first thing we need to do is we need to add the SPE plus ZPE. So those are these two numbers. So this is equal to that plus this. Double click that. So now I have the SPE plus ZPE. Also, I need the SPE plus ZPE plus the H correction. You have to be very careful here that the H correction in Gaussian, it includes the ZPE, but the number we brought from ORCA is actually, it doesn't include that number. So when you need to calculate the enthalpy, the H, you need to add actually these 3 numbers, the SPE, the ZPE, and this small number of correction. So this equals to this plus that plus that. So now we need to copy this. Now I have here delta E activation and delta H activation. I also have delta E reaction and delta H reaction, which I assume you now for delta E activation, that simply equals to, because I'm calculating that with ZPE, okay? So this means that ZPE correction is included. So this is equal to the products. Oh, sorry, the transition state. So what is the transition state? The transition state right here is right here. So it's actually this number minus that number. For delta H, it's equal to this number for the transition state minus that for the reactant. For delta E, for the reaction, it's equal products minus reactants. So that's silane plus the hydrogen minus that for the MMS. And for the delta H, that's going to be the enthalpy one. So this is for the hydrogen plus the silane minus that for MMS. Okay, so I get all these numbers in Hartrees. In Google, you can Google the conversion between Hartrees to kilocalorie per mole. That's 627.5. So I've just multiplied this number with 625, and I have find. This is a very shallow reaction, by the way. The delta E delta H is close to that of activation energy. So this is the number I get. I hope that you do the tutorial and you do the same. There's something I forget to tell you, is that the shape of the transition state. So when you click on the transition state on Avogadro, the log file, wow, it looks like that. Now what he did is actually he found you a transition state where these 2 hydrogens are actually good to go, and he also elongated this bond a little bit, because the bond in silane, the CSI bond in silane, it's actually a little bit longer than the parent molecule. Avogadro does not show you right now the frequencies, so I have used Chemcraft, the program I told you to install. Let's see what is going on here. So I'm gonna try, and then File, and then Open, and then I'm gonna open this transition state file. It looks different here, but watch this. There is a vibrational frequency. Of course, people who took computational chemistry course with me, they know that the first 6 frequencies are 0 or negligible. This one is negative. It's an imaginary frequency. Beautiful, you see? This is the 2 hydrogens vibrating in a way that they want to escape the molecule to form hydrogen molecule and the silyl. Okay? The other frequencies, of course, are positive, and they correspond to other coordinates. If you open the parent molecule in Chemcraft, the monomethylsilane itself, so File, Open, and then monomethylsilane, should be this one. It also shows you the frequencies, but none of them are negative. They are all real frequencies, and that's what should be a neutral, happy molecule should have. They have to have all positive frequencies with no problems. Only transition state they have to have 1 and 1 single frequencies. So I hope that you enjoyed this tutorial, and you might give it a shot. And if you have troubles, you are welcome to contact me. And this is my email. I'm gonna write down here: i.badran@najah.edu. Okay, so you are always welcome to contact me with this email. I'm gonna be happy to respond to your questions. I'm also on ResearchGate. You can also communicate with me through ResearchGate. Thank you so much, and have yourself a beautiful day.